Listo, ¿no?
Tú me dices cuándo empezar.
Ya estamos live, ¿vale? Puedes empezar, Nicolás, sí.
Okay. So, hi everyone, and welcome to this session of the Latin American Webinars on Physics. So today, I'm Nicolás Bernal from Universidad Antonio Nariño in Bogotá, Colombia. And today we're super happy to have Okay, so we're super happy because we have today Professor Ezequiel Álvarez from the International Center for Advanced Science, ICAS, in Buenos Aires, Argentina. And we'll talk about the Intelligent Archive. So please, Ezequiel, you can get started.
Okay. Thank you very much, Nicolás. Thank you very much, all the hosts and everybody here. It is a pleasure to be part of the Latin American webinars, which already became international webinars. So I'm going to share the screen so I can start. Okay.
Please, sure.
So please confirm. Can you see the first slide?
Yes.
Okay. So I will talk about Intelligent Archive, sort daily papers by learning user topic preferences. So although this doesn't look as a physics paper in the first sight, it is physics in two sides. From one side, because of course that having an enhanced access to bibliography can enhance the scientific performance of each of us. And also because the machine learning technique I'm going to talk about is an unsupervised machine learning technique, which is not very popular yet, and I think it is very powerful, and it can be used to look for new physics, as I will show you in the talk. So the talk follows these motivations. No? We have every day, as we can see, that the daily archive releases are increasingly large, and we want to have a best access to bibliography where we can put the papers that are more interesting to us in the top. Then we have also a growing interdisciplinary works, and there are new machine learning techniques available. So with these motivations, we pursue the following goals. Okay, the first goal, it is, can we make it to sort the daily archive papers according to our preferences? It is very important to stress that. It is according to each user preference and not to popularity of the paper. So it has to learn which are your preferences, your personal preferences. We want to develop algorithms which can add up many categories. So sometimes you are interested in Astro pH and HEP pH, and reading both categories, it is very difficult. So a machine helping you to select the papers which are more likely to the ones you are interested, it is very useful. And we want to develop a site, which is going to be free always, which has to do with you read the papers in this site instead in the archive, and the machine learns as you click which paper you want to open. So the main goal, the most difficult goal here, it is whether can we sort the archive papers according to each user preferences. So the outline of the talk is the following. I'm going to first talk about topics model, which is a concept introduced 20 years ago, which has to do with a different way of accessing a huge number of documents. Okay. Then I will talk about the machine learning technique, which is an unsupervised machine learning technique, which is LDA, Latent Dirichlet Allocation. It is very important that when we talk about this technique to be used in physics, that it is unsupervised, as I'm going to tell later. Then I will talk about how to apply this technique on the archive. I'm going to talk about the whole corpus of paper, the subtleties, the topics, and all this. And then I will talk about the site itself, which is called iarchive.org. Then I will talk shortly about some plans for near futures. And I will talk about physics using LDA. And here is something that I will stress all the time, that we know how to use supervised machine learning in physics. And using unsupervised, I think it is the way to go, because when you use supervised machine learning, you are based on Monte Carlo simulations and then neural network or boosted decision trees, but you are all the time based on Monte Carlo simulations. The truth is that when you're looking for new physics, new learning technique that can recognize patterns on which after you can pay attention and try to and then the conclusion. Topic model, it is a concept introduced 20 years ago by the time of the explosion of the internet, and the question that people addressing this problem was how to index a number of documents in a clever way. So that's topics model, which is kind of the central thing about this talk and about iArchive. So say, for instance, that you have a huge number of books or documents and you want to index them. There are many ways to do it. The question is whether there is one that is more clever. One possible way, of course, it is to index the books by their subject. You have a quantum mechanics books, a quantum field theory, and a cosmology book. Corpus of documents from their topic to extract 1,000 top probability distribution over the dictionary. You don't know genetics occur together. Machine learning technique would be able to extract topics initially occur together. So
something's happening YouTube, but for some reason YouTube is not.
It's a kind of a glitch.
If you go directly there,
if you go into the YouTube,
you have to do two things. So let's okay. So Roberto or Nicolás, were you able?
so
I don't think it's from my side.
We cannot restart the broadcast with the same link. Create a new event with the new. So this stuff we can do it. And YouTube is just.
Yeah, it's definitely a bandwidth problem.
But it's not from us, because for instance, if I have a problem, my video is just collapsed, but you guys can keep going.
Yeah.
Now, so on YouTube, and it's low, but they are still receiving that. So the point is that, okay, live.
Yes.
Right? But the information that we're sending, conversation right now, will be on.
We can cut that. So yeah.
Okay.
Ezequiel, could you please go back a little?
Back a little bit.
Yes,
like
and also please minimize this. Like, could you please taking it out because it's
like this.
Or just with. So, yes.
But hold on.
Like yes, perfect.
Now it's like excellent connection. But
yes,
it's also this video is private. So I don't know what's happening.
Okay. Do you want me to keep on going?
Hold on just 1 second.
What do you mean that is private? I'm looking in YouTube and I don't see the private. Nicolás.
I think now, yes, the YouTube is hearing all our previous discussion.
Okay. Well, that's fine. So let's back up a little bit and let's keep it up.
Okay.
And then what we can do is, Nicolás, you're the host, so please start recording on the cloud, and then if it doesn't work, we can pause the video, even if this is not working. And we apologize for our viewers. This is unexpected.
Yes, I think the YouTube there is delay. My colleagues are telling me that there is a delay just in YouTube.
Yes. Okay.
So I think we can just keep going, and that's it.
Yes. Sorry about that.
Okay.
So let's.
Sorry, again.
So I keep on going?
Yeah.
Okay. So sorry about that. Okay. Let's go back a couple of slides. I was saying that the clever way to index a huge amount of documents, it is by creating these abstract topics. What I was saying that if you have, for instance, many books or many documents, the topic model algorithm would recognize that there are words which occur frequently together. For instance, in this here, it will recognize that gene, DNA, genetic occurs always together and with some probability distribution, whereas also, for instance, brain, neuron, nerve would also occur together. So it is realizing the algorithm that along all the documents, there are topics, and that each document, it is constituted by the topics in different fractions. That would be, you have all the documents and the topics, which are less than the documents, okay? And each document has something from art, something from budget, children education for each document. So the topic model is a data mining technique for discovering, for extracting topics in documents. And each topic is a cluster of words that frequently occur together. So for instance, the topic art would be 2% of the word art, 1.3% of the word sculpture, music, colors. Whereas other topics, for instance, children, would have a different weight on all the words in the dictionary. As a matter of fact, it will be more weighted in kids, young, play, game, ball. So these are the topics which are contained in all the documents. This is a natural language processing algorithm, but then it has found many applications in biology, genetics, bioinformatics, and very recently in the last 2 years in physics as well. So I will first talk about the natural language processing to apply it to archive, and then we'll talk about physics. But let me talk about a little bit more detail first about the machine learning technique, which is called LDA for Latent Dirichlet Allocation. The idea behind this is that each document is a multinomial distribution on the topics, and that each topic is a multinomial distribution on all the words of the dictionary. So more precisely speaking, what we have, it is that for each document, having a given fraction of the topics has a probability which is a multinomial, which depends on some parameters theta. Whereas for each topic is defined by the probability distribution over all the words of the dictionary. So if you have a set of 100 words, which is the probability of having them depends on, in each topic, no, depends on the parameters beta. And the clever thing that they have done is to assume that there is a Dirichlet distribution over the parameters of the multinomial distribution, that it is a probability of a probability. And here it is, I mean, when you can quantify the probability of a probability, you can apply Bayes' theorem, okay, to get which is the most likely of the parameters. So the idea here, very shortly speaking, of course, this is a very complex paper, but the idea is that you feed the algorithm with all the papers, and the algorithm has some priori parameters, and it can get which are the most likely topics in the documents. Schematically speaking, this works like this. So you have the theta, which are the hyperparameters of the per document topic proportions, and you have the beta, which are for the topics. So to make run the algorithm, you put some priori parameters, eta and alpha, which by reading each document's word, every time the algorithm gets a word, says, okay, this word has a probability of being in each one of the topics of the document. And then in each topic, it has a probability of being each word of being the given word in the dictionary. So using this recursively many times, it can construct which are the most likely topics in the corpus. And that is what it does, the LDA algorithm. Of course, much more complex, no? But this is the idea that it is possible, at least. Okay, so I will now talk about how we can use this LDA on the archive. Okay, fortunately, this is a very complex algorithm, but the guys of Python have done the libraries to make it more easy. So it is amazing how many things you can do with Python with all these things, no? The idea behind applying LDA to the archive is the following. Each paper is a mixture of different scientific knowledge, which is close to be true, because when you do a paper, you have like 5 collaborators, 4, 3, or whatever, and each one is a specialist in topics in different ways. So when you're collaborating, when you're doing a paper, you are mixing the topics of each one of the collaborators, which sounds reasonable. So we decided to try to apply this on the archive and to see how does it come out. So the idea in the archive is that you have the archive divided by archive categories, okay? We're gonna take the documents only the title and the abstract. We will not take the full document. So we're gonna build an LDA model using only title and abstract, okay? We use the script of Python, which are the typical libraries like Gensim, and many others, but mainly Jensen has included the LDA algorithm. And it has many details that you can read in the paper. As for instance, we had to adapt the libraries because there are many technical words, for instance, ADC, ADA, CP, whatever, that were usually thrown away by the algorithm as it comes in Python. And once we do this, we can construct the LDA model. We have done this in 2 steps. In the first step, we have mixed together all these categories: AstroPH, gravitation quantum cosmology, HEP-TH, and HEP-PH. And mixing all these papers, we have a corpus of documents. And as I told you a couple of slides before, we ask now the algorithm to recognize topics. You have to put the algorithm how many topics you want. That it doesn't realize it because I mean it's not defined. These are abstract topics. But in this case, we require 4 topics. And we wanted to see how well the human supervised division of the topics corresponds to the unsupervised machine learning division of the topic. What we have found is that if you do that and then you keep only the paper of one category and you see the weights, the distribution of weights of the topics, you see that each category has one topic which peaks in one. So what we see here is that there is a great unsupervised agreement between topics and categories. Okay, this is a nice result, which would be expectable, but it's nice to find it. So here are the ROC curves showing that the categories are correctly chosen. So let me stress this. What we have done is to use totally unsupervised machine learning discovery of 4 topics when you take a corpus of documents, which are the 4 categories. And we have seen that the algorithm extracts the 4 topics that correctly correspond to the categories. Okay, let me show you which are these topics which have no title, no label, but just abstract topic. But it is immediately to see, for instance, that this one, the last one, it is HEP-TH, no? Theory, field, gauge, string. Okay, this one, black hole field, is gravitation quantum cosmology. This one, star observation, galaxy mass, it is AstroPH, and this one that begins with model is HEP-PH. Observe, there are many things. Observe that the word model, it is in HEP-PH, and it is also in HEP-TH, but it is with different weight. So topics do not rely on keywords, but rely on this, that it is a more complex structure called topics. It is important because if you rely on keywords, you could have never distinguished one from the other, or you would have distinguished it, but not as efficiently as here. Okay, so the topic is something much more complex than keywords. That's what I want to transmit. So the next thing we have done, it is okay, now we're going to construct an LDA model, but for each one of the categories in the archive. So one LDA model for HEP-TH, one for HEP-PH, Astro, and GR. Okay, and we have constructed asking like about 30 to 60 topics. And here there is what we call pizza plot, where each point, it is a document in the corpus, and each slice corresponds to one topic. So we put the point in the topic, in the main topic of the document, of the paper, and we put it closer to the center if the topic, if the paper has homogeneity of topics. Let's say that it's a mixture of all the topics together, and closer to the crust outside here if it is only one topic in the document. This pizza plot tells us that we are doing fine because we don't have papers in the center and we don't have papers in the crust, meaning that we don't have papers which are composed homogeneously of all the topics, and we do not have papers which are one topic only, monotopics, which is what we wanted to avoid in the construction. So after doing this, for instance, in AstroPH, let me show you the topics. There are like 40 topics, and you can see here the topics, and you can recognize, you can label them with your own word. For instance, here, whole, black, gravitation, wave, binary, merger. This is talking about black hole merging. This one here is about talking about instrumentation, right? image telescope resolution optic. And here you have another one that talks about black holes. It's black hole field model equation. But here it's not talking about the black hole merger, but about black hole theory. So what you see is that the topic model, you can really feel the power of the topic model here, because the topic 2 is talking about black hole mergers, and the topic 39 is talking about black hole theory, even though they share many words. So as you see, the LDA algorithm can distinguish two topics which are very similar and realize that they are different, because the guy who works in black hole theory, okay, it is interested in black hole merger, but he's working in black hole theory. You can imagine a person who doesn't know physics, that you give them a couple of books about black holes, and it's going to take it a long time to realize that there are two topics. One is merger and one theory. I'm just trying to transmit the power of the technique. Okay, so once we have this, we have everything down, because we have, for every paper, we have a vector, which is the weight on each one of the topics. Let's say 40 topics. And every time a person reads a paper or writes a paper, we have the vector of the paper he wrote or he read. And what we do is we construct a personal vector for this author, which is the sum of all the vectors that he read, and then normalize. And to know how much a user it is interested in a given paper, in a given new paper, you have to do the inner product between these two vectors. And the closer is this inner product to 1, is that there is more likelihood between the topics he likes and the topics of the paper. So that is the secret of sorting papers according to each user preference. So let me recall, you have to record which are the papers that the user likes as he or she clicks in the site, and you construct his or her personal vector, and every time comes a new paper, you do the inner product. So you can sort paper for each user. You have numbers sorted between 0 and 1. So using this, we have constructed a site which is very similar to Archive, but with an I before, no? Intelligent Archive. So let me show you how this works, and you can try it. It's already working since like 3 months ago, and you can try it and take a look. How does it work for you? Our experience is that works. Okay, you take your own conclusion. So let me tell you a little bit about the iArchive site. When you first log in, when you first get there, you're going to see something like that. To log in, you can register. When you register, you put your minimal things that we need for you to keep track of of the paper you like. It is important that you put your real first name and your real last name, because the system, it will look in the archive database and recognize which are your papers. So after you do that, if you put the student Weinberg, for instance, here, you choose which categories you want to follow, and then you confirm which are your papers, because eventually you have some author which is similar to you. Once you do all this, you put save changes, and you can enjoy the iArchive papers, which are now sorted according to your personal preferences. Not only that, you can choose also a data slice. For instance, you went to vacation for 10 days. When you come back, you have to read either 500 papers, or you put it here, and it's going to sort the 500 papers for you. Okay, it's going to be less work. Okay, the papers are sorted according to the inner product I have told you before, and the system keeps on learning as you click. And the algorithm is such that the more recent papers you click or you have written, it weights a little bit more that paper. So it can recognize which are the topics you like more recently than the one you liked it before, but also keeps track of the one you liked it before, but with a less weight. And at the end of the list, you will see that there are other papers, which it doesn't show you the abstract, but just the title. You can expand the abstract, and the algorithm keeps on learning when you expand an abstract. Okay. Since a week ago, we have inaugurated a new option, which is a daily email. So you can subscribe to the daily email, and you, just as you receive the Archive daily email, you can receive the iArchive daily email, which has the same number of papers of the categories you choose. You can choose which categories you follow. and they are sorted according to your preferences. And that's very comfortable, and it has a nice, more visual on the mail to read it on the phone and the tablet, everything. It tells you the score, it has each paper, and you can click either here to go to archive or either here to go to the PDF. Okay, and okay, we have made it a little cheat. So you can receive the paper like 30 to 40 minutes before receiving the official archive paper. That's an interesting feature also. Okay, and let me, okay, that's about iArchive. I really hope you can try it and test it. Now let me tell you about the launching of the iArchive. This happened in February 6th. We put the paper in the archive called iArchive. So the first impression was very nice. We reached 500 users all worldwide in 4 days. Of course, this didn't grow up that fast later. Nowadays, we are in 860 users, of which more than the half never log in. That's the truth. So we are like about half of that. And okay, people are using it, and we have a growing rate of about 10 a week, or sometimes 15, sometimes 5. Okay, but about 10 a week. That means that I think that it is more important than the launching, because it means that it is working and people are commenting to their friends and colleagues, hey, you take a try of this because it worked fine. I appreciate more this is slowly growing after a long time we have launched it. Okay, let me tell you a little bit about some feedback we had after we launched it. Okay, we have many very popular people talking about the paper. We have a field medal also talking about it. And for instance, here people of the community of quantum information said something that we didn't understand at the beginning, but it is very interesting. The quantum information community use sorting by voting since many years, which is side rate. So from our community, like AstroPH, HePH, our these categories, it is truly not important how popular is a paper, but really how, if does it describe nature or not. We have seen so many papers with so many sites and which are wrong, and it would have been so much saving of time not following popularity, right? But however, other disciplines, as quantum information, it is important popularity, because at the end, these are disciplines which end in a technology innovation, and that has to do with popularity. I mean, what people think about something, but not in our field, okay? And okay, also people talking about size-wise. I'm going to talk about these other sites now. Here there is one guy, very interesting guy, who said he will not use it because doing such, he will put it in another bubble. So of course, it is a nice contradiction, because if you don't use it to try something new, you are already in a bubble. But we also have so many other positives of people here from CERN who were, I mean, the nice thing about iArchive, once you use it, is that many times it puts you a paper at the beginning of the list, and you say, this title has nothing to do with what I do. But when you read the abstract, you realize, oh, okay, here it is a Z prime that I do use. So it makes the job for you of reading the abstract and sorting it, because sometimes the title is not what it maybe corresponds to do, but many times it has topics on which you are interested, but it is not in the title. So sometimes you get amazed at how does it work. So let me compare very briefly iArchive to other similar platforms, because of course we are not the first one trying to do this. You have SciRate, Arxiv, ScienceWise, okay? The first one, ScienceRate, as I told you, here you have in Quantum PH, you have that each paper are voted like 52 times, the most popular. But if you go to HePH, it has only one vote, the most popular, meaning that in fact, different disciplines, our discipline, HePH, HePTH, with this, do not really care about popularity, but other disciplines do care. And it is okay that they should care, because they're more linked to technology innovation, okay? So it has some pro, like popularity, some contra, which is the bias. Archivist, also, it is a very nice platform, but again, for instance, they say here, there is a sorting of the paper, and these articles are based on your preferences that you have to sign in to reorder the articles based on your preference, so you can influence this table. So it is something weird, as if you would be interested in influencing what others read, which again is not what we are looking for. I want to say that all these are very good, but they are different goals, different objectives. Science-wise info, also, this works very nice because this has kind of a topic modeling, but the difference is that the topics are made by the users. So users have the freedom to create topics and to say this paper has these topics. This is more similar to what we do and works very nice, sorry. But the con is that having the users making the topics introduce a bias which could be potentially dangerous because users want to, let's say, they want to put their topics. In the machine learning, you have unbiased. So here again, the prose is very complete and sophisticated, tackles all categories, and it does more than just sorting. It has some more features which are very interesting. Our cons is that I think that conceptual topic is not good, and it is biased by supervised learning. And the other thing, which is not less, is that being sophisticated, I'm not sure that having a tool that helps you to read the archive paper should be sophisticated. At some point, you want to do physics, you want to do papers, and you don't want to really get into an involved world of bibliography. You just want to do papers. So it's like to have it simple. And that's something we kept in mind, like less is more. Okay, this Benty Fields is not very known, but it's a very nice web, which has a very nice features. You put a button, and you just show you the figures of the paper. That's very interesting. What I would say the bad thing is that uses an algorithm based on keywords and supervised machine learning based on keywords. So this kind of algorithm cannot distinguish the topics. Let me go back on this because this is one of the most important enhancements of iArchive, right? For instance, let's say keywords versus LDA. When we model a HEP-PH, we can recognize these 4 topics, which all have the word QCD. But if you see the ordering of the other words, you realize that one corresponds to lattice QCD, one to precision QCD, one to effective QCD, and one to phase transition. So LDA can distinguish, can disentangle different topics with the same keyword. And that is very powerful. And that's why they use it for the Wikipedia, and they used to use it for Google, this LDA. Okay. So this is about more or less of iArchive. The very short one slide for the plans on near future. Okay. Well, these were the plans. Now with the coronavirus, the truth that we don't have no more budget to do nothing. So we want to do, but we have in mind how to do a method where you can really access many categories at the same time and put some, and you can define threshold and weight, so it can give you the paper that you are interested in and not 300 papers a day. Okay, we have an idea, which is bibliography 1. You provide to the iArchive site a paper, and it will give you all the related papers in the corpus, but using the LDA algorithm to find the related paper. Let's say each paper has a vector. It will find all the paper whose vector has an inner product larger than others. And this is another idea which sounds very interesting. Is let's say that in the iArchive, we provide you a little form where you can put a title and an abstract of a paper you think you may write, or you are writing, or you are trying to write. And the site will return you all the papers related to that idea, to the topics you put in that abstract, in that proportion. So that, I mean, it is a new way of finding bibliography. This is all to be done. Okay, and we also thought about going beyond LDA using other machine learning techniques to make it much better each personal taste. But of course, these are all complications. Having it as it works now, which is simple, it works very fine. Okay. Now, let me talk about what I have promised you before, okay? This is physics using latent Dirichlet allocation. The first thing that comes to your mind, surely, is how you want to do physics if this is something which was created for natural language processing. And in physics, you have a dictionary, right? You have events. So the idea here it is that you have to you have to adapt a physical situation to a dictionary. How you do that? Let me show you. So we have done this. We have considered new physics searches LHC using LDA. This can be done also in AstroPH or in other fields. So if you have many events, you can say that you have signal and background, which are two topics. And if you have more than one background, you may have more topics. So with this idea, we have applied to a real LHC scenario, which is 4 top searches. Okay, the idea is that you can construct a corpus of documents using the events, and then use LDA to extract the topics. And you will have something that, without using Monte Carlo, it can label that there are 2 topics and that some events are more likely to be signal and other more likely to be background, where it's not defined what is signal or background, just 2 topics. So in 4 tops, why we haven't published this paper yet, but we are using it. The idea is you have 4 tops at LHC. It's a very difficult state because you have many particles. It is impossible to reconstruct. You have very bad Monte Carlo simulations, and the background have very large uncertainties. So this is an ideal field for LDA. So what we have done is the following. We consider each event as a document, and we have to adapt the dictionary to the particles in the event features. We have done this like this. Instead of, this is a word. B1_100 means that the leading bottom jet has 100 of PT, or the being of 100 between 150. The second one is, so we are we are converting the document, the event into a document after defining a dictionary. So if you have many events, you will be recognizing that these features about the particles, which are words, begin to occur together. And the LDA will extract some topics, which it is realizing that it's a different kind of event according to how frequently occur together these new words we are defining. So what we have done, it is, we have simulated 4 tops and the 2 main backgrounds, which are TTH and TTW. And we have run LDA and required to extract 2 topics or 3 topics. So as you see, we are here simulating the physics with the Monte Carlo, but then we use this just to simulate. We do not use Monte Carlo at all, but we use LDA to extract the topics from these simulated events. And what we find, it is very encouraging, because when we restrict to the events which are signal, for instance here, we see that the 2 topics defined by the LDA really have different weight on signals. Whereas in background, this difference is not that large, okay, but here it is very large. So the end of discussion plot, it is this, which is the arrow secure, and we see that the the red and blue line here are very similar, meaning that the unsupervised machine learning search strategy is fairly equal to the full Monte Carlo cat-based search strategy. So the unsupervised machine learning is doing as well as, let's say, a human-made based on Monte Carlo. And that's very interesting because the Monte Carlo may have bias, but the unsupervised machine learning does not have bias. It's really distinguishing 2 kinds of events. So similar examples and application can be thought everywhere. Okay, the idea is to convert a physics scenario into a document. Many events, every event in a document, and then understand which is the best dictionary you have to use to run LDA. So the conclusions, well, are very short. We have created this new platform, ircap.org. I really hope you can use it and enjoy it. You're going to be surprised of how much better you can do physics when you have the paper sorted for you. We have used topic model application through LDA. Okay, the main feature of this is that it is unbiased because it is machine learning, machine defined topics, and we only use the information about you and not about the popularity of the paper. So it's important to say this will not put you in a bubble in a sense that everybody's talking about a given subject. Then I am trying to talk about this, but I am not really interested about that. It has to do with which are your preferences. And again, all the papers are there. You can read them all. Okay, it has many useful prospects for the near future, as I had talked. We will try to go beyond LDA. And maybe one of the most important things that we are finding now is that it has many applications in physics. We have to really begin thinking machine learning and supervised for finding new physics, because supervised machine learning, it is really biased by the Monte Carlo, which we know that has many, I mean, it is a very important tool, Monte Carlo, but also has many limitations. Okay, thank you very much for listening. I hope you were there because I was talking to a computer alone here.
Yeah.
Okay.
Yes, we were here.
Okay.
Okay. Thank you. It's Nicolás.
Sorry, guys, I'm back.
Okay.
I had some problems with the connection. Can you hear me?
Yes.
Okay. So thank you very much, Ezequiel, for this super nice talk. And I first want to apologize to you and to all the viewers because we had some, well, these problems with the, well, technical problems between the connection between Zoom and YouTube. But okay, now it's working. So are there questions from the audience first, for instance?
I have a question for Ezequiel. So first of all, Ezequiel, super interesting all the system behind how to order this, to sort the archive, indeed, because it's a huge work to check out the archive every day. And I remember one of the bad stuff that has archived. I mean, not bad stuff, but how you were saying in some part in your talk, if somebody goes for a holiday for 1 week, then if you want to recover which paper were sent to archive in the last week, you cannot arrive because it's like you can check just at most 5 days or something like that in back. Yeah. I mean, according to the daily sorting. So one of the questions that I was wondering is when you make all this analysis, if you can include or have you tried to check how topics are evolving, like with in terms of the time when the paper was released or the preprint was released, like because this is could give you some information about not the popularity, but where the people is working nowadays.
Yes. We can do that. Yes, we can do that. We haven't done it, okay, because it takes time, but actually, well, Manuel and Federico, who are here, who are some of the authors who have done all the work, they've been playing with that. And it is very interesting. I mean, it came out very interesting things about the topics, how sometimes, I don't know, supersymmetry goes up, then goes down. Mm-hmm. And yes, it is very interesting. You can really play a lot with this. But of course, it's not physics, but it is to see the bibliography investigation, which is interesting at some point. Yes. This is a tool that, because you are converting the whole archive into an algebra of vectors. So you can do everything with that once you have done this. Yes, especially this what you're mentioning.
Yeah, another maybe a little bit technical question about the iArchive, because once I remember I was playing just with the API of Archive, and they have a kind of a strong restriction about the number of requests that you can do per day or something like that per time. So because if you have to fetch all the information for Archive from time to time, maybe you could get some blockage from the website itself.
No, but we get the information only once, and then we have all the database, all the papers in our database. So
yeah, but if you want to go back in time, I mean, if there are papers pointing to elder papers in Archive, you have to go to fetch, and if you are making a kind of the bibliography search in backwards.
We have downloaded the last 10 years of Archive papers using the API. The API allows you to go like, I don't know, by 200. I mean, you can put it to work and it begins downloading like 200 and 200. And we have downloaded the last 10 years of each one of the four categories. So we have all that in our database. So it is, and every paper it is converted, it is already translated into a vector of the categories. It is the paper and also in the cross categories.
And Roberto, I think you can also notify the archive that you are doing this and explaining them, and then just take out the flag like they allow. You just specify the details and then they just allow.
Ah, okay. Okay, thank you.
But we didn't need to do that, eh?
Yeah.
We just download everything. I mean, I can pass you the Python script, which you put it to run and download from. Like it takes like, I don't know, like 4 or 5 hours, because it waits like a couple of seconds between every batch, and it downloads the last 10 years.
So,
Okay.
I mean, okay, other question first, because then I'm gonna ask.
Yes, in the chat, you can see a question from Diego Restrepo. He's wondering if this method can be applied to the problem of ambiguity of authors.
Ambiguity of what?
Authors. I mean, if two persons have exactly the same name, if so with this algorithm you can disentangle them.
No, you cannot. I mean, when you start, it allows you to choose the names, because if you have the same last name and the same initial, you're going to put you both papers, and you can put this is mine, this is not. Yes, but that is an ambiguity. I don't know. It's very hard to do it. I mean, yes, there was a guy from China who complained to me, and I said, I'm really sorry about that, because yes, he had, there was another Atlas author with the same name, and it was very hard. Yes.
You can imagine.
But what you can do, you can put all to no, and then, I mean, if you want the machine, the algorithm to learn for you, you can take a slice of 10 days and begin clicking the papers you like. And for instance, you have put your name incorrectly. It's not the end of the world, because you just choose a slice of 10 days and begin just clicking the papers you like. And after you have clicked like 20 papers, the algorithm already begins to work very good. So that you can do if you have a name which is very equal to some Atlas author or CMS author.
I see. Thanks. I can see another question from. Oh, sorry.
Sorry, I have one.
Please,
so is there a reason why HEP-X was not included? Because that would be tremendously useful.
Yes, the reason is that there are very, very few papers HEP-X a day, like 6, 7 papers. But yes, even though at the beginning we didn't include, we could include it like with the same model of HEP-PH. That would be the clever thing maybe to do it, to put it together with HEP-PH, because I mean it is the same topics. But the reason is that there are so, I mean, to use only one for HEP-X doesn't make sense, because you have 5, 6 papers a day. But maybe to include it in your list of HEP-PH would be nice. And also, now that you say this, Astro-PH has the thing that has like 6, 7 subtopics, and they have like 100 papers a day. So maybe we thought about like saying, okay, I read Astro-PH, but I don't want instrumentation, for instance, or something like that. These are things to be improved, but require some dedication, time, and cross-checks. Mm-hmm.
Super, thanks.
Okay, so there's a question from Thomas Bailund. He asked, how does Arxiv reason about the privacy aspect of collecting information about users' preferences?
Collecting information of the users.
Exactly.
Well, nothing. I mean, we have a vector of every user. We have a vector in the database, which is private, which is very strongly private. Actually, let me tell you something very funny. The night we went on the archive, we had an attack to the database. The same night, like 20 minutes after the paper came out, and okay, we have protected it very, very strongly with some guys who do this kind of things. And okay, all we have about the users, as you can see when you log in, we only have the name and the email, nothing else. And you can also put a fake name and a fake email. And what we have is a vector of preferences. That's all we have, and we have it very well kept. Of course, nothing is unbreakable in the internet, but in the worst case scenario, someone can know what you have read, but that's it. I mean, I think it is, the database, it is very strongly crypted. and locked. That's nothing to worry. And of course, we do not share with anyone, nothing at all. And you can subscribe to the email, and that is, of course, not compulsory. I mean, when we have installed this new email feature, we thought about sending email to everybody, but we said, no, we cannot do that. So we just let people to keep on knowing that it is this feature, which is very useful. And you just have to, if you are interested, you go and click. And then you have a button that you, when you receive the email at the end says unsubscribe, and you unsubscribe and you're not receiving emails anymore. So that's how we manage security.
Okay. There's another question from Diego Restrepo. He's wondering about the possible advantages or disadvantages of using the full text of the document and not only the title and abstract.
Yeah, I think that would be, definitely an advancement. I mean, it would be great because many times you talk about things in the article and you don't put it in the abstract because you don't have enough space or you consider it secondary. So I think that definitely using the whole text, it would be great. Okay, it requires another kind of things because we have downloaded from the archive database only title and abstract. We were trying and it works very nice, but surely we are missing something without including the whole text. It is true. Yeah, this is improvable in that sense. It would be great to include it with a different weight, of course. One thing is the title, one thing is the abstract, one thing is the text. But you may find something that you cannot find in some other way. Yes, yes. He's right. It would be a nice improvement. Mm-hmm.
Okay. My questions, Javi, we are missing you. Otherwise, Diego Restrepo has another question now, this time about coronavirus. He's curious about what can be learned if we apply this to this overwhelming literature of 1,500 papers about the coronavirus.
Well, yeah. Of course, we can distinguish topics, no? I mean, you have to train a model. Yeah, you cannot apply it straightforward. You have to first get the 500 papers of whatever number of papers and apply a model, and then you will distinguish that these papers have topics, okay, and sort them for you, of course. I mean, it would be a nice way to also to keep the track of all what is being done. I mean, yes, it could work. I mean, if someone is working in that, the number of papers daily there, it is huge. So to keep track, it would be very useful, okay, but it requires some time, no, to use it. To train the model to all this, it requires human resources for machine learning.
Yeah. Okay, there's another question from Diego. He's wondering if you plan to release part of the software used in this iArchive.
Well, yes, we could release something, but we cannot release all because, and the thing is, if we release all, people would know which are the topics. And if you know which are the topics, you can write an abstract to make your paper appear first. For people who work at LHC, there is a topic called LHC, and there, for instance, in HeadPH, there are some topics which are very popular. And if you know exactly how this topic is formed, it is the danger of having people, how do you say? I mean, to try to cheat. It's just as people try to cheat on Google, try to cheat here to make your paper appear first. So it is better than the topics are not known, and not known the number of topics to avoid any kind of singularity. But yes, all the libraries are open, and it is essentially what we have to, I mean, once you get to learn the GenSim library, it is essentially to apply that to the abstracts, also with a little subtlety of which are the keywords that you want to include in the topics. We would be happy to discuss that with Diego. So Diego, you can write to us. We can share you as much as we can. So if you want to do this for the coronavirus, would be great. Yes.
Excellent. Any further questions?
I have another 2 questions, if I
Sure.
can make 2. So one of the, I mean, let's start with the small one. Let's say, imagine that there is some PhD students or people that roughly have 1 or 2 papers in archive? Is there a way to because maybe they don't have enough statistic to have a good selection of paper? How do you have plans to kind of have an extra suggestions of paper for those people, or
Yes,
they have to accumulate more paper in order to be able to?
No. The extra suggestion for these people, it is to open a 10-day slice of data, and you will have there like, I don't know, 500 papers or 400 papers, and keep on going and just click on the papers not read it, just click on the paper where you would be interested to read or have to do with your topic. So after you click on like 20 papers, the system begins working pretty fine. And then every day you will have a sorted batch, even though you have, so the system is fed by 2 sides. By one side, the papers you have written, and by the other side, the papers you read, you click. So if you haven't written too many papers, you have to, let's say, to enhance the other side, and read many and click on many papers you like, and that's the way it works.
Okay, so and the other question that maybe is the most tricky part, because of course it's not, I don't know, it is not part already of iArchive, but usually it happens with people when you submit a paper to archive, even though you make all the bibliography research and so on and so forth to make the most representative bibliography of your paper, then all the time there are some papers that were missing to be cited. And then people write you, please cite my paper, so on and so forth. So is it possible, or in the future, maybe it's not just an idea that you would think if it is possible, kind of to give just reading your paper and the bibliography of your paper to suggest extra paper to complete the bibliography of your paper in the sense to avoid the uncite people, because usually that happens in some topics, that all the people cite just this very old paper of the topic, but they are completely outdated citation, and they become like super popular in the field, even though they are uncited because of the same relation, because 30 years ago, why I'm gonna to have an unbiased bibliography of that is just going to be submitted.
Yes, thank you.